So let's go ahead and start with problems like this. Let's do the following, maybe 3 problems. Sure. I want to simplify to one expression, cosine of x times 1 plus, what we got here, tangent squared x. I think I might be reading that wrong. No, that's right. Okay. So let's see what happens here. Typically, when I'm writing this, I'm going to think of things as sines and cosines. I feel like that's usually the most efficient way to get there. This is cosine of x times 1 plus tangent squared is sine squared x over cosine squared x. And then we almost always want to get the common denominator to be able to add fractions together. So I'm going to write this as cosine of x times cosine squared x plus sine squared x. I should have said it's cosine squared x over cosine squared x plus sine squared x over cosine squared x. Simplifying a bit, this is going to be cosine of x times cosine squared x plus sine squared x is just 1 over cosine squared x. You can cancel a cosine, or you can multiply it out, or you could say it's cosine over cosine squared. And then you can cancel a cosine on top and a cosine on the bottom. Now, you shouldn't stop at 1 over cosine. You could maybe argue technically it's one trig function, but we really want the trig function that isn't kind of it's nothing but a trig function. You should be the reciprocal of the trig function. So I should rewrite this as secant of x. Let's look at another one. Again, stop me if you have questions or you have a comment or something. Let's look at this one. Let's see, what is it? 1 minus sine of x times secant of x plus tangent of x. Okay. So again, secant and tangent, I want to rewrite in terms of sines and cosines. That's not always required. It just feels like the easiest thing to do to me. So I'm going to write this as 1 minus sine of x times, let's see, secant of x is 1 over cosine of x. Tangent of x is sine x over cosine of x. Great, we can add this together. They already have a common denominator. So this is equal to 1 minus sine of x times 1 plus sine of x over cosine of x. All right, now we can multiply. So this is 1 minus sine over 1, if you like. Top times top, bottom times bottom. The bottom is just going to be 1 times cosine of x, which is cosine of x. The top is going to be 1 minus sine times 1 plus sine. So 1 minus sine times 1 plus sine is going to be 1 squared, which is 1. The middle terms cancel. You get a 1 plus sine and a 1, you get a 1 times sine and a 1 times negative sine. So you get a sine minus sine, which cancels. And then you get a minus sine times sine, which is minus sine squared x. 1 minus sine squared x is equal to cosine squared x. And then cosine squared x over cosine x, we cancel a cosine on the top and a cosine on the bottom, and we get just cosine of x. Just something that I saw a couple times, just want to make sure that nobody makes this mistake. I did see occasionally people write something like 1 minus sine of x is equal to cosine of x. That is not true. It is true that 1 minus sine squared of x equals cosine squared of x. But it is not true that 1 minus sine of x is equal to cosine of x. So just be a little bit careful with your trig identities there. Let's see. Let's do one more and then we'll talk about some rational function graphing. So let's say I want to simplify cosine of x over cosecant of x minus sine of x. Okay. So that's cosine of x over cosecant is 1 over sine. And sine, I know I'm gonna have to subtract these together, so instead of writing just sine, I'm gonna write minus sine squared x over sine of x. Right? We know that we can multiply sine by sine over sine to get sine squared over sine. Now we're gonna make this denominator one fraction. So we can't flip and multiply until we have made the thing in the bottom one whole fraction. So write this as cosine of x over 1 minus sine squared of x over sine of x. At this point, if you wanted to, you could flip and multiply, although I would probably simplify first. But I would say that you could totally write this as cosine of x times the reciprocal of this. So sine of x over 1 minus sine squared of x. I probably first would have changed 1 minus sine squared into cosine squared, but it's okay to not do that first. So then this is going to be cosine of x times sine of x over cosine squared of x. And then I can cancel a cosine and get sine of x over cosine of x, which is tangent. So that's kind of the process, right? You're always writing things in terms of sines and cosines. You're often using the trinity 1 minus sine squared equals cosine squared, or 1 minus cosine squared equals sine squared, or sine squared plus cosine squared equals 1. And all those kind of come up. They're all the same, just written differently. Let's graph some rational functions. I like there was something else in there. Oh, interval notation. Let's do some interval notation, and then we'll graph some rational functions. So to my mind, interval notation really comes up when we start talking about finding the domain of something. So like I could say I want to find the domain of the following functions. Let's say f of x equal to, let's make it interesting, sure, the square root of x plus 9 over x squared minus 6x plus 8. Sure. Okay. So we got a couple things to contend with here. We have to think about both where the denominator might be 0 and where the square root, the stuff inside the square root might be negative, right? Those are problems. So we need 1 to exclude where the denominator is equal to 0. Okay, well, that's going to factor. That factors is x minus 2 times x minus 4 equal to 0. So we want to exclude x equal to 2 and x equal to 4. So at this point, I like to start drawing my number line. Be like, okay, so far on my number line, I know I don't want 2 and I don't want 4. I'm not going to color everything else in yet because I don't know I want everything else, but so far, everything besides 2 and 4 is fine. I don't care about the denominator being positive or negative. I just care about the denominator not being 0. And then we also have to look at the insides of the square root. So the insides of the square root have to be greater than or equal to 0. In this case, it's very easy to solve for x and say x is greater than or equal to negative 9. So we also know that at negative 9, we want to include negative 9 because x should be greater than or equal to negative 9. So we want negative 9, and then we want everything to the right because that's the side that's greater than or equal to it. So I want everything over here. I want all that. I want all that. I want all that. I don't want this. So my domain here, and again, we're always trying to write it from left to right. So the leftmost thing I have is negative 9. So it's going to start at negative 9. And and then it's going to go up to 2, but then at 2, I have a break. So don't include 2. So including -9, I write a bracket. Excluding 2, I write a parentheses. And then on the other side of 2, between 2 and 4, I want everything between 2 and 4. This is literally every number between 2 and 4. 2.1, 2.0005, pi, 3, 3.7, right? Any number between 2 and 4, that's in there. Just not 2 or 4 themselves. And then finally, we want everything to the right of 4. So everything from 4 to infinity and beyond. Right? That's the whole thing. So 2s and 4s get parentheses because we want to exclude them. -9 gets a bracket because we want to include it. And infinity always gets a parentheses because it's not a real number, so you can't include it. Let's do another
one. James, I have a really quick question.
Go ahead.
For which type of problems is it that we have to check if the numbers are like positive on the number line? I can't exactly remember what we did that for, but we'd go through a process to see if like our x.
Yeah, yes, we're right there. You're asking the perfect leading question to my next problem.
Okay, thank you.
So let's say I want to find the domain of. Let's do that, sure. Yeah, let's yeah, we'll make it fun. F of x equal to, I'm gonna make it kind of complicated. The square root of x to the 3rd times x minus 8 squared times x plus 5 times x plus 7 cubed all over x squared minus 1. Okay, cool stuff. So we can write it down, but we can probably all see that we need to exclude what 2 values? What makes the denominator 0 here?
Square root of 1.
Which is equal to what?
+1 and -1.
Right. So I will say the square root of 1 is just equal to +1. But the solutions to this equation, x squared minus 1 equal to 0, are both plus or minus 1. So x squared equal to 1, you get x equal to plus or minus the square root of 1, and then the square root of 1 is just 1 itself. So we're excluding those values. All right, so we already know we don't want 1 and -1. Yeah, but I'm not going to write those on there yet. So typically, well, let's do the second part, and then we'll talk about why we want to do the second part first. So we also need to say that the insides of the square root, which is kind of complicated, x cubed times x minus 8 squared times x plus 5 times x plus 7 cubed, we need that to be greater than or equal to 0. So we need to put the things that make it equal to 0 on the number line. That's going to be 0, 8, -5, and -7. So we have 1, 2, 3, 4, 5 different regions to check whether it's positive or negative. And the reason I don't want to write the 1 and the -1 here is because I don't need to check in between them. Nothing changes there except that the denominator happens to be 0. So I would say if you have this kind of thing where you have to check a bunch of things, whether it's positive or negative, don't include anything else on your number line until after you've done that. So pick a number larger than 8, like 9. Positive, 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 positive. Pick a number smaller than 8, like 4. Positive, negative, but the negative number squared is still positive. So positive, 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 positive. Or as I like to say, the 8 came from this factor. This factor had an even multiplicity, so the sign doesn't change. You can also think about the graph having an x-intercept with an even multiplicity and the graph bouncing off and staying positive. Okay, then 0, well, again, we can pick a number like -1. -1 cubed is still negative. -1 minus 8 squared, that's always going to be positive. So negative, positive, positive, positive. Or 0 came from a factor with an odd power, so the sign changed. -5 comes from x plus 5 with an odd power, so the sign's also going to change. You could also pick a point like -6. -6 cubed is negative. -6 minus 8 squared is positive. So negative, positive. -6 plus 5 is negative. -6 plus 7 is positive. So negative, positive gives me a positive overall because it's two negatives. And then finally, over here on the other side, -7, we can pick something like -8. Negative squared is positive. Negative cubed is still negative. So negative, positive, negative multiplies to a negative. Okay, we want the positive parts. So we want this and this. But then we also want to make sure that we exclude -1 and 1. Now I will point out -1 is already excluded, right? It's in a region that we're not going to pick anyway. But 1, we definitely have to make sure we exclude. So we want to include the endpoints because we want it to be greater than or equal to 0. So we want to include -7, we want to include -5, we want to include 0, we want to include 8. So here's how we're going to write this. And I guess, right, if you want, you can like scribble in the parts that you want. Okay, I should circle that one too. So let's see, I want everything from -7 to -5. It's my domain. And then I want everything from 0 to 1, inclusive of 0, exclusive of 1. And then I want everything from 1 to 8 and 8 to infinity, but there's no breaks. So I really should just write it as 1 to infinity. Questions about this one?
Could you explain how you got the positives and negatives again?
Sure. So all I'm doing what I'm doing is, I'll do it up here again. So from the part that has to be positive, right? This expression here has to be positive or 0. I'm taking all the numbers that make it equal to 0. So x equals 0 makes this part 0. X equals 8. X equals -5. X equals -7. Those are the places where the sign can change from positive to negative or negative to positive. So those are the things that are going to go on my number line. So 0, 8, -5, -7. And then in between each interval or each 0, I'm picking a value of x to plug into this expression. So over here, I picked x equal to 9. Here, I picked x equal to 4. Here, I picked x equal to -2. Here, I picked x equal to -6. Here, I picked x equal to -8. And then I tested the expression at that point to see if it was positive or negative. Now, I'm not actually looking at the value. I'm just looking at whether the product is going to be positive or negative. So I plugged in 9. 9 cubed is positive. 9 minus 8 squared is positive. 9 plus 5 is positive. 9 plus 7 cubed is positive. And a positive times a positive times a positive times a positive is positive. For 4, 4 cubed is positive. 4 minus 8 is negative, but a negative number squared is still positive. In fact, a negative thing cubed or squared is always positive. So so this part here, this part's always going to be positive. So I get positive, 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 positive. The whole thing is positive. Then I pick -2 and I plug it in. A negative number cubed is negative. Positive. -2 plus 5 is positive. -2 plus 7 is positive. So it's a negative times a positive times a positive times a positive. So it ends up being negative. And then between -5 and -7, I picked -6. -6 cubed is negative. This part's positive. Negative 6 plus 5 is also negative. Negative 6 plus 7 is positive. So I get a negative times a positive times a negative times a positive, which is positive. Finally, I pick negative 8. Negative, positive, negative, negative. The whole thing is a negative because it's a negative times a negative times a negative times a positive. And then we excluded negative 1 and 1. So that's how I'm doing it. I'm writing down the values that make this inequality equal to 0. And then I'm testing points in between. I'm not testing these points. I know those points make it equal to 0. I'm testing points that are in between each of these things. Why was the domain 1? And so I think you're asking, Fernando, why did we exclude 1? To answer the question I think you're asking, well, so it says 0, 1 here because, right, we do not want the number 1, right? I'm going from 0 inclusive to 1 not included. And then I'm starting back up at 1 not included all the way to infinity. And the reason I don't want the number 1 is because the number 1 makes the denominator equal to 0. Other questions? Let's do one more. And then we'll graph some rational functions. Let's say, where did my pen go? Sorry, I'm trying to, got like one good pen. So let's say our function f of x is equal to, let's see what kind of thing can I make up here? Log base 3 of, that's like fun, x minus 5. Oh, that's like, no, let's do 5 minus x cubed times x minus 1 squared times x plus 3. Okay. So I want to find the domain for this function. So similar, but not exactly the same as a square root function or an even root. When you have a logarithm, doesn't matter what the base is. When you have a logarithm, we have to say that the insides of the logarithm, so we have to say that 5 minus x cubed times x minus 1 squared times x plus 3, that has to be strictly greater than 0. It can't even equal 0. So that means we're not going to include any of the endpoints. So let's find the values that make this equal to 0. So the zeros here are x equal to 5, right? Because 5 minus 5 equals 0. It's not negative 5, it's positive 5. X equal to 1, and x equal to negative 3. Okay. So then we're going to put those 3 numbers and only those numbers on the number line in the right order. So, right, not 5, 1, negative 3, but 5, 1, negative 3. And then we're going to pick. We're going to pick values that are in between. So I should say, if there's 3 zeros, then there's going to be 1, 2, 3, 4 intervals. There's always one more interval than the number of zeros you have. So we're going to pick something like x equal to 7, x equal to 3, x equal to 0. I like picking 0 if 0 is a choice. And 0 is between negative 3 and positive 1, and x equal to negative 6. You can pick any numbers you want as long as they are not the actual numbers that we've already written there. Okay, so now I want to determine if it's positive or negative. So pick a number bigger than 5, we picked 7. 5 minus 7 is negative, and the negative number cubed is still negative. 7 minus 1 is positive, 7 plus 3 is positive. So I have a negative times a positive, which is going to be negative overall. Okay, then between 1 and 5, we pick 3. 5 minus 3 is positive, a positive number cubed is still. So you might notice I never say a positive number to a power, because once your thing is positive, if you raise it to any power, it's still going to be positive. So, right, 5 minus 3 is positive, and yes, a positive number cubed is still positive. 3 minus 1 is positive, 3 plus 3 is positive, so the whole thing is positive. Picking 0, 5 minus 0 is positive. 0 minus 1 is negative, but a negative number squared is still positive, and 0 plus 3 is positive. So it's going to be, I said what, positive, 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 it's going to be still positive. And then finally picking negative 6, 5 minus 6 is positive. Negative 6 minus 1 is negative, but it's squared, so it's still positive. But negative 6 plus 3 is negative. So you have a positive times a negative, which is negative overall. We want the positive parts, but since it's greater than 0 and not equal to 0, we don't want the endpoints because the endpoints make it equal to 0. So our domain here is this interval from negative 3 to 1, exclusive of either endpoint. Right? We don't want the endpoints. Union 1 to 5. We don't want anything over here because that makes it negative. We want it to be positive. We don't want anything over there for the same reason. All right, let's graph some rational functions. So let's say we want to graph f of x equal to, sure, let's do x squared minus 6x plus 8 over x cubed. Yeah, we'll do that. X, let me think for a second here. Let's see, x minus, sure, x. Oh, come on, brain it up. Sorry, I'm making other problems. Let's see. We can do that. That would be silly. No, that's done. Let's do that. Let's do x cubed plus, yeah, 4x squared plus 4x. That seems, yeah, that seems fine. Okay, so if you're graphing a rational function, it's also a good idea to factor it. So the top is going to factor as x minus 4 times x minus 2. I already used that one today, I know. The denominator is going to factor, well, clearly I can factor on the x. I'm left with x squared plus 4x plus 4, which factors as x plus 2 times x plus 2, or x plus 2 squared. Okay. So let's find the y-intercept. So at x equals 0. At x equals 0, we get f of 0 is negative 4 times negative 2 divided by 0 times 2 squared. What's that?
Undefined.
Right. We don't have a y-intercept at 0 because we have a vertical asymptote at 0. So right, if you get division by 0, we're like, oh, no y-intercept. Okay, x-intercept, we will have some. So x-intercept, we set the top equal to 0. So we're going to set x minus 4 times x minus 2 equal to 0. We're going to get x equal to 4 and x equal to 2. And they're both going to have a multiplicity of 1, meaning they're going to cross. Let's find the vertical asymptotes. So the vertical asymptotes are going to be setting the denominator equal to 0. We're going to get x equal to 0 with a multiplicity of 1, and we're going to get x equal to -2 with a multiplicity of 2. Meaning at 0, one side is going to go up to infinity, one side is going to go down to -infinity. And at -2, either they're both going to go up or they're both going to go down. And then the horizontal asymptote, we do have one. What is the horizontal asymptote here? Is it 1 or is it 0?
When the bottom is bigger, there's none, right?
Well, no, I wouldn't say it's no. So when the top has a higher degree, that's when there's no horizontal asymptote.
Oh,
When the bottom has a higher degree, that's when the horizontal asymptote is
0.
0. The way you can think about it, right, is again, when you're finding the horizontal asymptote, you're asking what's happening as x gets really, really, really large or negatively large. If x is really, really large, since the denominator has a higher power of x, this denominator is going to get bigger much faster, and the overall fraction is going to get small because you're going to have a number divided by a much larger number. Okay, that's it. So let's graph it on the other side here. So let's put all of our features on the graph, and then we will try to graph it. So we have x-intercepts at 2 and 4. Well, that's not 2, that's 1. We have no y-intercept. We have vertical asymptotes at 0 and -2. And we also have a horizontal asymptote at 0. Normally I wouldn't draw these in, but okay. And we know that at both of our intercepts we're going to cross. And we also know that at this asymptote, it's going to be one side up, one side down. And this side, they're right the same, both up or both down. So we actually need another point here, right? We don't know where we might be above or below the x-axis. So I'm going to plug in x equal to 1. And again, right, my original function was x squared plus minus 6x plus 8 over x cubed plus 4x squared plus 4. Right? That's what I said? Yeah. Okay, so we plug in 1. F of 1 is going to be 1 minus 6 plus 8 all over 1 plus 4 plus 4. Which is going to be, let's see, -5 plus 8 is 3 over 9. So 1/3, so positive. So at 1, we're getting a positive number. Okay, great. So that means that we have to go this way. Right? Because there's nowhere between 1 and 0 where we could have gone on the other side of the x-axis. And then we're going to cross here and we're going to cross there. Then we don't just keep going that way because we have a horizontal asymptote. So we have to turn around. Say, well, okay, I don't know where, but somewhere it's going to turn around and then get closer and closer to my horizontal asymptote like that. All right. On the other side of this vertical asymptote, we know we have to be going downwards because we know that the 0 was from an odd powered vertical asymptote. Or you can check another point. You can check -1 if you wanted to. Look at f of -1. It's going to be 1 plus 6 plus 8 divided by -1 plus 4 plus 4. I feel like I'm making a mistake somehow. Oh, that's a 4x. Sorry, not a 4. That's not a problem. So that's going to be -1 plus 4 minus 4. So that's going to be 1 plus 6 plus 8, which is 15, over -1 plus 4 minus 4, which is just -1. So when we plug in -1, we get -15. I'm not going to make it look that extreme. I'm just going to say it's definitely negative. So we're going down this way, and then we are having to go back that way. Right? There's no x-intercepts to cross the x-axis at. And then over here on this side, we know that this was an even powered one, right? This was the odd one where they're going the opposite direction. This is the even one where they're going the same direction. If you don't like that, you could also plug in something like -3, although it's kind of a pain to plug in. If you plug in -3, you're going to get something gross, right? You're going to get 9 minus 18 plus 8 over -27. 4 times 9 is 36 minus 12. So you get -1 on the top, and that's interesting. I'm making dumb mistakes again. I plugged in -3, right? Right. And I got, oh, that should be a plus 18. I am making dumb mistakes again. And plus 18 plus 8 is going to be 35. Over -27 minus 12 is -39, plus 36 is -3. That's negative something. So yeah, it's still down here. And then as we move to the left, we have to get closer and closer and closer to our horizontal asymptote. Okay, let's look at one more example. We got time for one more. Let's see. I'll just start. So let's say we want to graph f of x equal to 2x minus 5 times x plus 2 over x minus 1 squared. Let's find all the things. Y-intercept. F of 0 is, let's see, 0 minus 5 times 0 plus 2 over 0 minus 1 squared. That's going to be -10 over 1, so -10. X-intercepts. So at the top equal to 0. 2x minus 5 times x plus 2 equals 0. So 2x minus 5 equal to 0 gives you 2x equal to 5. X is 5 halves. X plus 2 equal to 0, you get x equal to -2. And that's it. And they're both going to cross again. For my vertical asymptote, I'm just setting the denominator equal to 0. So x minus 1 squared equal to 0. You're going to get x equal to 1. It is going to have a multiplicity of 2, meaning both up or both down. And then finally, for my horizontal asymptote, so if you multiply this out, the top is going to be 2x times x is 2x squared, and then minus 5x plus 4x is minus x, and then minus 5 times 2 is minus 10. And the bottom is x squared minus 2x plus 1. The degrees are the same, so the horizontal asymptote is the quotient of the leading coefficient, which is 2 over 1, which is 2. Okay, let's graph it. So let's see, I've got a y-intercept of -10, which I'm probably not going to make. I'm just like, okay, there's -10. Sure. No, we would not have a value of -1, because if you solve this equal to 0, right? If you solve x minus 1 squared equal to 0, you get x minus 1 equal to 0, and then you get x equal to +1, because you add 1 to both sides. If we had -1, -1 minus 1 would be -2, which would not be 0, which would mean we won't have a vertical asymptote there.
Okay.
Plotting these points, I'm going to go 1, 2, 3. So x is -2 and x is +5 halves, which is between 2 and 3. And then let's see, I've got a vertical asymptote at 1. And I've got a horizontal asymptote at 2. So starting my y-intercept, I know I have to go this way. There's no other choice. And then on the other side, since I know my vertical asymptote is an even degree or multiplicity one, I know I'm in the same direction. So if I'm going down here, I'm going down there. Or you can plug in 2. If you plug in 2, you get -1 times 4 over 1, which is going to be -4. When we come up, we hit our point, we cross, and we get closer and closer to our horizontal asymptote. Same deal on the left. When we go left, we're going to hit our point, we're going to cross, and we're going to get closer and closer to the horizontal asymptote. That's it.